Hi kids, again, sorry I'm not there to say do your last lesson of this unit with you in person, but more sad that I don't get to say goodbye to you before the break. So anyway, the homework is in the book and the sub has the rubrics for your homework. So you should get that and look over all the AP rubrics. I don't have it for one of the problem. It's not an AP problem. But check your answers with each other. Like, how did you justify that first problem's absolute min at either 1 or 7? And then look at the AP rubrics for the other problems. And I hope that I had 2011 rubric on there, but I don't have a copy of the packet at home. If I don't, though, please feel free to look at the AP Central. You can literally Google what are the answers to 2011 problem, whatever that was. Because again, I think that one had that more common twist that they're starting to do with first fundamental theorem, is where the accumulation function has a constant or a linear function added to it. So the substitute also has a first fundamental practice handout that's going to go with the rest of these slides. So if I was there, I would have gone over some of these rubrics with you. Here, making sure again that you look at things like this one where they're talking about the interior analysis and that you must consider the endpoints. Down here, a choice of g of 1 is a point of inflection and the other one is not. Okay? Don't forget to justify when it asks to, and right, make sure, look at where they're using fun in here, right? The first fundamental theorem is all in here. Again, the next one. Here again is an AP style, take a point away from you if you don't have the correct area, if you're not summing correctly, right? Here, look how the explanation that you can also describe it with the first fundamental theorem here, or you can do it as you can describe it by I'm accumulating these many integral values, positive and negative. Notice here they're like, even if you start discussing at x equals 5, which is the endpoint, they're not going to pay attention because they gave you an open interval here. And look at down here, this is only worth 2 points, and what this notation down here means that the maximum you can get is the 1 out of 2. If you thought about 0 or 3 and discarded the 3 because of the corner, right? That's the max. You are automatically out of half of the points available. Also here, the maximum you can get is 1 out of 2 if you discarded any values because of that corner. They're absolutely hitting this. Be careful. So again, I'm not sure if your packet includes this or not, because again, I don't have a copy and I added this one, but I wanted to make sure that here, part A is pretty routine, where they're just going to give you points for the values. And notice that g prime of x I did with you in class, that it's 2 plus f of x. Then here, notice that for these 3 points, you have to say where the derivative is equal to 0. Now, setting this derivative equal to 0, right? 0 is equal to 2 plus f of x, right? So that's what it means to set the derivative equal to 0 here. Then identifying interior candidates, because they only gave you, right, interior candidates for the calculus, and then answer with justification. C was only worth 1 point, right? It looks like it's got too many words, right, for 1 point. but it is just asking for the point of inflection. But notice you can't just have an answer. You have to have the answer with the reason. So if you just have the answer with no reason, you lose that point. They don't do half points. Part D, right? Here's the slope of the secant. The slope of the secant, that's algebra 1. You're getting points for algebra 1 right there, right? And then only 1 point for the explanation, but to why it's talking about the mean value theorem and the conditions. F must be differentiable. F must be differentiable at each point in the interval. However, f, the function I'm looking at, is not differentiable at -3 and 0. So again, you see another place where they're asking you and letting, you know, you have to be very careful when you're looking at those corners and cusps on these graphs. Are they asking you about the original? Because then the corners and cusps don't indicate non-differentiability. But if they're asking you about the derivative of the graph you're looking at, then it does talk about does indicate non-differentiability. Kind of can get me, right? Get your head spinning, I know. All right, notes. This is, I don't know if it's actually in the new version anymore, but it used to be in the old version. And I was like, oh, are you joking, right? A desert island and you're thinking about calculus? Come on now. So I'm like, dork. Anyway, so remember the fundamental theorem of calculus, right? I was talking about the first part. And I kind of do that. I kind of break it up into part 1 because I think about the graphical part of this. Part 1 is the graphical interpretation, right? So now I'm going to focus on the algebra. Now, algebra with the first fun. That doesn't change the first fundamental theorem. Here it is. If, then, as long as you're continuous on a closed interval, you have the capital, this function is an accumulator, then the derivative of the accumulator is the integrand. Just to repeat, thinking about the derivative of an integral undoes all derivative and integral notation, and you are left just with the function. But I want to focus on the derivative of the integral, the variable of integration. You're taking a derivative with respect to x. And notice that when you are done undoing the antiderivative, x shows back up in the function, right? The derivative variable, right, matches the upper limit of integration. The lower limit of integration is a constant, but remember what happens when you're taking the derivative of a constant, right? The constant goes away. So all you did, you really didn't do any thinking. You just copied the integrand over. You copy, paste, but you replace the t with the upper limit of integration, which was also the variable of differentiation. Whee! Whee! So, look at this problem. If someone says evaluate, now I'm going to tell you in May, when I teach you how to do integration, you're going to be tempted to work inside out. You're going to be tempted to do the integral, do this integration, and then take a derivative. Waste o' time, hun. Waste o' time. Right? I remember where the eraser was, and now I forget. Was it here? Screen. Oh yeah, here it was. Erase. Ha ha ha. Sorry, had a little moment there. What somebody is asking you to do is to take the derivative of an antiderivative. That's like saying take the square root of a square. Right? Sorry. So you know what I do with this? I say to myself, self, that's a derivative of an integral. Then I say to myself, self, does the variable of differentiation match the upper limit of integration? Derivative, the variable of the derivative matches the upper limit of integration. Is that true? Check. Next I ask myself, is the lower limit of integration a constant? Check. If I've got all three of those checks, how you take the derivative of an antiderivative is to copy the integrand over and take out the t and replace it with the upper limit of integration. Done. No math. Done. Copy, paste, replace the t with the upper limit of integration. Easy. Uh-oh. Problem. I say to myself, self, I have a derivative of an antiderivative, but the upper limit of integration does not match. Chain rule. Didn't see it coming, did you? Didn't see it coming. Got to use the chain rule when you're taking the derivative. I want you to think of x squared being in place of x. So guess what I have to do? I'm going to copy over the integrand. I'm going to replace t with x squared, and then I'm going to spit. There goes the x squared. Spit out the derivative of x squared. Woot! Done. Uh-oh, another problem. You have the derivative of the antiderivative, but what's the issue? The lower limit of integration is not a constant, but the upper limit is. Oh, what can I do? What can I do? I hear it. Come on in, properties of integration. Come on in. Change the sign of the integral and reverse the limits. So negatize the front, flip the limits of integration the way you want them, copy the integrand, replace the t's, all of the t's you see, with x. Oh, I forgot to put a green square around that dt, didn't I? Got it? Easy peasy, with a twist. Oh no, this is a bummer. I have a derivative of an antiderivative, but what's the issue? Neither limit of integration is a constant. Come on in. Come on in, properties of integrals. Come on in. Come on in. Split the integral into two parts, right? If you can integrate, you are continuous, right? So if you got to be continuous to integrate, so if you can integrate, you're continuous. So use the property of integrals and split it up. So notice I kept the d, right? I kept the differentiation, right? I still am taking the derivative of a sum of antiderivatives. And notice what I did here. I kind of sort of skipped a step, right? I should have, up here, what I should have done is I'm taking a 2x and an x squared, and I want to make two integrals. Oh no, I guess I didn't really skip the step, right? I replaced the 2x with the 0, and I moved that to an x squared, and then I replaced the x squared with the 0 and made that a 2x. Right? That doesn't really flow though. Right? If I'm going to use the properties, because the property I'm using is the integral from a to b plus the integral from b to c is equal to the integral of what? A to c. So I want to use that here, but what's the issue? Those limits have to match. Do they? No. Now you might ask me, why did I choose the constant 0? And I'm going to answer you, why not? Right? So I'm continuous over all real numbers. If I want to choose to split a domain somewhere, why wouldn't I choose 0? Right? If you want to pick another constant, go ahead, because guess what I'm doing? Taking a derivative, so who cares? Right? So it does not matter. It does not matter what constant we use as long as the constant is in the domain of the integrand. And it is. Now look at what I've done. Right? I left the first integral the same, but what did I do to the second one? Right, I switched the 0 and the 2x, I switched their position, so how did I have to pay that price? Negatize. Now what did I do? Right, going from 0 to x squared and going from 0 to 2x, negatize it. So now I'm actually taking the derivative. To take the derivative, right, I want the constant at the bottom, so I've got the constant at the bottom here, right? Sorry, I need to back up. I think I confused you a little bit. I have my 0 and 0 here so that I can use my property, which is a to b plus b to c, right, is 2x to x squared. But then I had to negatize here so that I could get the constant at the bottom. Once I have the constant at the bottom, I'm going to copy the integrand over, replace the t with the upper limit of integration, spit out the derivative of the upper limit of integration. I'm going to copy the integrand over, replace the t with the upper limit of integration, spit out the derivative. So see what I did there? Replace the t with the x squared, spit 2x. Replace the t with 2x, multiply by 2. Woot! Don't bother getting a common denominator. I'm all done with that. Right, so there's a little picture of, right, I don't really care if the constant we use is between a and b. Right, it doesn't really matter. Right, the integral, just a little picture here that the integral from 2 to 6, I can say is 2 to 4 plus 4 to 6, but that's also equal to 0 to 6 plus 2 to 0, right? Take a moment to look at all of these and convince yourself that they are the same. The property of integrals where I can split up. I have an equation. I can split these up any way I really is convenient for me. All right, so here's some examples. No, this would be no calculator. If I define f of x as an accumulator function, what's f prime? Right? F prime means you took the derivative of this side, so you have to take the derivative of this side. How do you take the derivative of an antiderivative? Copy the integrand over, replace the t with the x squared, but then since that's not just an x, what do? Spit the derivative out. Here's capital F. I want the derivative. I have a constant at the bottom and a function in terms of x in the top. So take the derivative of both sides. The derivative of -3 goes away. Copy cosine over, but it's cosine of 2x plus 1. Spit the derivative of the inside. How about this one? Right? Again, you're taking the derivative of capital F, which means you're taking the derivative of an antiderivative. But this time, my constant's in the wrong place, right? My constant's at the top, so what are you going to do? Negatize. Copy over the integrand, I'm sorry. Tangent. What are you going to replace t with? X cubed. What are you going to spit out? 3x squared. Right? Not so bad, as long as you realize that you're taking the derivative of an antiderivative. So I'm going to give you some time, right? Take a moment and see if you can do this one. Constant at the bottom. Function in terms of x there. So the derivative is just going to be the square root of 3 plus cosine of what squared? 4x squared. Spit out what? 4. So clean that up. 4 times the square root of 3 plus, and you don't have to clean it up unless you're matching multiple choice. Now, to take the derivative, second derivative, that's old news, right? You don't have any integrals yet. I mean, any integrals left. So how do you take the derivative of that function? It's 4 times the square root. So that's 3 plus cosine of 16x squared to the negative 1/2. Spit out the derivative of the inside. What's the derivative of the inside? The derivative of 3 is nothing. The derivative of cosine is negative sine times 16x squared. Spit out the derivative of 16x squared, which is 32x. OMG. All right, so now this is a handout, and these examples have a little twist. They're ones that we've seen more recently on the AP exam. So look at this quick. This looks like, what the heck? You have to realize you've got a function, and the function y is an accumulator function. A is a constant. C is a constant. And here is the variable x. So they want dy dx, and they want you to, they've given you dy dx, excuse me, and they want y. Well, how do you get y by itself? It's got a derivative around it. How do you get rid of a derivative? Yep. Take an antiderivative. So the antiderivative gets rid of all the derivatives and the antiderivatives and leaves me with just y. So I've got e to the x tangent x dx. Oops, no, this has to be t dt. But now I have to figure out what a is. What's my constant? And they want me to put x up here, right? So what's my constant that I can start at if y is equal to 0 when y is 8? So you say to yourself, properties of integrals. What's true about the integral when you know nothing about this function? You can't anti-differentiate this, but when will y be equal to 0? What's true? If x is equal to 8, how does this integral equal 0? That's right. This has to be 8. So y is equal to 8 to x of e to the t tangent t dt. Right? It all was about figuring out when an accumulation function is equal to 0. And if it's equal to 0 when x is 8, the only way to get that, the easiest way to say I want accumulator to be 0 is when you get nothing, when you go nowhere. So now what about this one? Think about this next one. What would you do? No skipping school. You want y, they want you to get y by itself, but y is wrapped up in a derivative. So what do? Anti-differentiate. Anti-differentiate. What happens when you anti-differentiate a derivative? The antiderivative goes away. But so does all the derivative stuff, leaving just y. So y is equal to the square root of 3 minus cosine, not of x though, of what? T, and then dt. Right? But I have to put something here and something here. So, what can I do? So let's look at the information they've given us, right? I'm going to go over here because I have more room. So when y is equal to 4, I have to integrate when x is equal to negative 3, the constant has to be something. So I think to myself, this would be easy if I was equal to 0, right? Well, ask yourself, what can happen right? If a was equal to negative 3, right, what do you get out of this integral if you go from negative 3 to negative 3? Don't you get 0 out of this part? But I don't want 0. What do I want? 4. So what can I do then? Right? If this whole red box is 0, but I want 4, what are you going to do? Yeah, add 4. So what does y equal? 4 plus the integral of negative 3 to x of the square root of 3 minus cosine t dt. Check your work. If you plug in x to be negative 3, don't you get 4? I think so. All right. Let's look next. Find the linearization. What does that mean? Tangent line, right? Point slope form. Y minus the y coordinate is equal to the slope, d word, x minus the x coordinate. Well, what x coordinate did they give you? They gave you a 0, right? So put a 0 there. So what is f of 0? 4 plus, start at 0, oh snap, go to 0, of, I don't care how ugly you are, function right here, don't care, don't care. If you don't go nowhere, what do you got? Nothing. So that whole thing cancels out. So what is f of 0? 4. Now, this is the slope. What's the d word for the slope? Derivative, right? So what is f prime of x? The derivative, what's the derivative of sum? It's the sum of the derivatives. What's the derivative of 4? What's the derivative of the antiderivative? Constant in the bottom, x at the top, so this is just going to be ln of x plus 1. What is the derivative at the point of tangency? What is ln of 1? 0. Oh snap, this is a horizontal line. Y equals 4. Next, find f of 2 if, whoa, where's my y, I thought this was going to be capital F equal, oh wait, my equal sign is way over here. What the heck? Find little f of 2. Where's little f? Ooh, little f is wrapped up inside an integral. How do you get an integral off of f? Take the derivative of the left side, but if you take the derivative of the left side, what do you have to do to the right side? That's right. Take the derivative of the right side. Isn't that clever? So clever. So the derivative of the antiderivative and the derivative of x squared plus 5 to the 1/2. What do you get here? The derivative and the antiderivative all go away, and you get f of the upper limit of integration equal to the derivative of x squared to the 1/2. Spit. Now, what's f of 2? Right? X over the square root of x squared plus 5 when x is 2. So you're going to put 2 there and 2 there, and you get 2 over square root of 9, which is 2/3. Woot! Right? Kind of crazy. Right? And these kinds of problems are going to get you in May if you don't practice and remember. And think, right? Anytime you've got any issues with derivatives, you need to undo an antiderivative or you need to undo a derivative, right? Always think of the first fundamental theorem of calculus. All right, have fun. Try that book work, and remember to look over those rubrics from last night's homework. And I will talk to you. I won't see you, but I'll talk to you again tomorrow.